Catalysts are really important in chemistry as well. And catalysts, what they do is they make reactions go faster. And they make reactions go faster by essentially lowering the energy of activation. So you can see on the left versus the right, it's a catalyzed pathway versus an uncatalyzed pathway. So on the left, they threw a catalyst in. The energy of activation barrier, the height of E sub A, was certainly lower than the height of the uncatalyzed pathway on the right. And that's an example of what the reaction does without the catalyst. Catalysts always are used up and they're recreated at the end. So when you have a catalyzed pathway, you will have two bumps in the pathway. You can see on the right, that was a single step, only one hump, if you will, in the pathway. But E sub A, when it's lowered, does make the reaction go faster, and that can be very, very important. If you make a good catalyst, you can literally become a millionaire, all right? Because, wow, having the right catalyst can be the difference between making a lot of product versus just tiny amounts at one time. So go into catalysts if you want to make money.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface. A significant source of air pollution in many cities is the emission of nitrogen oxides by gasoline engines. The problem is not as severe as it was a few decades ago, due largely to the advent of devices called catalytic converters installed in automobile exhaust systems.
In the old days, like 1970s for that matter, smog was a real problem, especially in heavy industrialized, high population areas like Los Angeles, stuff like that. A catalytic converter is a type of a way that you can remove the carbon monoxide and nitrogen monoxide from a car exhausts and make better for the environment, arguably, CO2, N2, and O2. And the catalytic converters oftentimes use platinum, nickel, compounds, palladium, stuff like that. So they're pretty expensive, but man, the effect on the environment has been fantastic. And having a catalytic converter for gasoline production cars is pretty critical, I would say, for us. It also creates less problems breathing for people that are sensitive to that kind of stuff. Making polymers, which again is a huge part of industry, almost always involves some type of catalyst as well. And again, polymers are when you take things like ethene and turn them into polyethylene, stuff like that. Pretty cool process. You can make acetic acid from methanol using the right catalyst. A carbon monoxide can be inserted between the carbon on the methyl group and the hydroxide OH part to make acetic acid. And then definitely, like I mentioned briefly before, all of the enzymes that you might be hearing about in biology if you're taking that class. Enzymes are just biological catalysts. They're able to make a lot of life processes a lot easier, which is pretty cool.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
Manganese 4 oxide, aka MnO2, aka manganese dioxide, which I don't like as much. But anyway, MnO2 is a real common catalyst for a lot of species. Most of the transition metals that are catalysts, they'll involve electron transfer temporarily to another species, and then they get the electrons back. So in manganese's case, I don't know for sure on this mechanism, but I would guess it's going from a manganese 4 maybe to a manganese plus 2, and then somewhere it goes back to manganese plus 4 to make MnO2 again. But again, if you have a catalyzed system, remember that it's a multiple hump system. So the black line with the higher E sub A, that's the uncatalyzed reaction. So hydrogen peroxide decomposing by itself into water and oxygen. With a catalyst, you will certainly have more than one hump, probably two. In the first hump, the MnO2 is somehow used up, and in the second step, somehow the MnO2 is recreated. The reactants and products energy are the the same. So this is exothermic either way, but it takes a lot less time because E sub A has been lowered quite a bit relative to the uncatalyzed reaction. Lower E sub A, faster reactions generally. This is a reaction where you can take iodine as a catalyst and it can turn cis-2-butene into trans-2-butene. So this thing right here is the cis-2-butene, and on the far right you have trans-2-butene. It doesn't state it explicitly, but that's what's happening. And there's several steps, and this has been studied quite a bit. The first hump is iodine, I2, going to iodine atoms, iodide, and then the iodide goes to the double bond. It basically breaks the double bond. So at the highest point, one of the iodines has broken the double bond completely. And if I remember right, the carbon, either one of them is deficient or they're both sharing. This stuff gets really science fiction in the middle. But anyway, by breaking the double bond carbons can twist. So cis goes to trans, the double bond reforms, iodide atoms go back to iodine, and you end up on the product side. Again, overall reactants and products energy, it's exothermic because products are lower energy than reactants, but the uncatalyzed reaction, pretty tough to do. All right. I think it was like 240 kilojoules per mole we saw in an earlier lecture to make that transformation possible. But if you add a little iodine as a catalyst, you get the catalyst back, and it only takes 115 kilojoules per mole. And that's a lot easier than a 240 kilojoule per mole or so value.